So we come now to another one of those unusual indeterminate forms. This is 1 to the infinity. This is actually one of the most important forms that we have, and it's one of the most important examples of L'Hopital's rule. So first let me start again with the question that I have with the other forms, which is, why is this indeterminate? Think about what you know. I mean, if we're truly raising 1, if we're truly taking 1 and just multiplying 1 by itself an infinite number of times, we would just get 1. But what we're really doing is we're taking something that's approaching 1 and raising it to the infinity power. So if you imagine something that's bigger than 1, like say 1.1, and you multiply it by itself infinity times, it just keeps getting larger and larger and larger, and you just get infinity. On the other hand, if you take something that's positive but less than 1 and you multiply it by itself, like if you imagine taking something like 4/5 and just multiplying it by itself an infinite number of times, it just keeps shrinking. You take 4/5 of 4/5 of 4/5 of 4/5, you just eventually get down to 0. So we don't really know which one is going to overtake the other. Is it going to be kind of the oneness of the base, or is it going to be the infinityness of the exponent? It's indeterminate, and we're going to need a technique to evaluate something of this form. So here, let's evaluate the limit as x approaches infinity of 1 plus 2x, 2 over x to the x. And what we can see is that as we let x approach infinity, this 2 over x is just going to be 0. So we have 1 plus 0 to the infinity, and this is in fact a 1 to the infinity form. We get 1 plus 0 raised to the infinity power. So here's how we do this. It's going to be a fairly similar technique to what we did last time. We're going to let L equal the limit as x approaches infinity of 1 plus 2 over x to the x. Now I'm going to take the natural log of both sides. Ln L is equal to the limit as x approaches infinity, or sorry, rather the natural log of that. The natural log of the limit as x approaches infinity of 1 plus 2 over x to the x. And I'm going to bring the log inside using the rule that the limit of a log is equal to the log of a limit. So this is going to be the limit as x approaches infinity of ln 1 plus 2 over x to the x. And then finally, but next I'm going to use that law of exponents to bring the x down. So that's going to be ln L is equal to the limit as x approaches infinity of x times ln 1 plus 2 over x. Okay, so now what do we have? We have a limit that is, since x is approaching infinity, I have infinity here, and then for the ln, I'm going to have 1 plus 0 inside the ln. The natural log of 1 is just 0, so I've got infinity times 0. This gives me an infinity times 0 limit, which we know is a L'Hopital's rule form. So by operation of L'Hopital's rule, I'm going to say that the limit, the ln of the limit L is equal to the limit as x approaches infinity, or sorry, this is not by L'Hopital's rule, I'm just rearranging the algebra. I'm going to turn this into ln of 1 plus 2 over x over 1 over x, like that. In other words, instead of multiplying by x, I'm dividing by the reciprocal of x. It's the same thing. So now I, in fact, have ln of 1, which is 0, over 1 over infinity, which is also 0. So now I'm actually ready to apply L'Hopital's rule. I'll just put the LHop out here because it doesn't really apply over this equal sign. So this is going to be the limit as L approaches infinity of the derivative of the top. That's going to be 1 over 1 plus 2 over x. And the derivative of 1 plus 2 over x is going to be negative 2 over x squared. So that's negative 2 over x squared. So by the chain rule, I have to multiply by that. And then the derivative of the bottom, derivative of 1 over x, is negative 1 over x squared. Okay, so this is, by L'Hopital's rule, I've asserted that this limit is equal to this one. Now I need to do a little cancellation. I want to focus on this part here. Negative 2 over x squared divided by negative 1 over x squared is just going to be 2. So this gives me ln L is equal to the limit as x approaches infinity of, this is going to, I still have this expression left. So I have 1 over 1 plus 2 over x. And this thing that I've circled here is going to simplify to 2. Now I'm really ready to evaluate by substitution, because what I have here is going to be ln L is equals the limit. Actually, it's not even going to be the limit anymore. I'm just going to substitute. This is going to be 1 over 1 plus 0 times 2, which equals 2. So I have the natural log of the limit is equal to 2. I raise e to both sides, e to the ln L, which is just L, that equals e squared. So there's the answer. L, limit, is equal to e squared. So notice the assertion here, by the way, is that the limit as x approaches infinity of 1 plus 2 over x to the x equals e squared. It's a useful fact to remember. It's actually a very important fact to remember for Calc 1, and especially going on to Calc 2, because we make use of it a lot, that the limit as x approaches infinity of 1 plus 1 over x to the x is equal to e. You'll also see this in the form like this. This is going to be x plus 1 over x to the x equals e. And if you turn it around, if I instead write x over x plus 1 to the x, which is another 1 to the infinity form, that equals 1 over e. These two facts together with this one. These are worth remembering, but you should also know how to do this operation to find the limit by L'Hopital's rule.